Hello, my name's Geoff Phillips. I'm a research scientist working for the Environment Agency in the UK. I've been involved with lake restoration for a number of years, and Stephen's invited me to give you my views on the role that geoengineering might have in lake restoration. I think Stephen invited me because I'm a member of the regulatory community in the Environment Agency, but actually what I want to do is to give you my personal views rather than those of the Environment Agency. So let me start by reminding you the extent of the challenge. We've already heard from Stephen that eutrophication remains a central issue for lakes. I've shown here what the phosphorus concentrations look like, taken from the European Environment Agency website. And you can see it's a particular issue in Central Europe. Indeed, in England, of the 274 lakes we monitor, only 71, that's 26%, were classified at good or high status for phosphorus under the Water Framework Directive in our 2013 assessments. The impacts of eutrophication, and therefore the responses, are well known. We get extreme events. Here we see an algal bloom, significant effects on recreation. We can get fish kills. We have ecosystem changes with loss of aquatic macrophytes, resulting in fewer macroinvertebrates, changes to fish populations as the food supply changes, and more recently we've realised the extent to which this influences wildfowl that use our lakes. So there's a strong desire by the public to improve our lakes, to remove them from the algal bowl we see on the top to the clear water, macrophyte dominated communities we would like to see. In addition, the Water Framework Directive has a requirement on all member states to achieve good status in its surface waters by 2015. So lake restoration is a target we all need to think about. We start lake restoration by looking at the catchment. And in the UK, we've been reducing phosphorus loads from sewage treatment works since the early 90s, largely the result of the Urban Wastewater Treatment Directive. You see here on the bottom left the amount of phosphorus discharged to rivers by sewage treatment works in England and Wales, and we see a substantial reduction from 1995 through to 2010. The result of that is that phosphorus concentrations in our rivers are now reducing, and we see the same thing across the whole of Europe. An example taken here from eastern England, one of the most eutrophic areas of the UK, we see the way that phosphorus has changed from levels of 1 milligram per litre is now somewhere approaching 0.1 milligram per litre. However, when you bear in mind that the highest phosphorus target for these four eutrophic lakes is around 0.05 milligrams per litre, there is still some distance to go. We also expect that managing eutrophication will get no easier. Future pressures and trends in climate will not aid us. We will expect to see an extra 10 million people by 2030 in England and Wales. We know agriculture and land use change will occur, with agriculture becoming more intensive. We're aware that climate change predictions suggest we'll get reductions in summer rainfall, reducing the flushing of lakes. We'll see higher temperatures with impacts on phytoplankton growth, change to fish populations, and thus reductions in the potential for top-down control through zooplankton. Eutrophication management will get no easier in lakes. To illustrate how difficult it is, I show you what progress or lack of progress has been made in delivering good status for all water bodies in England. The Environment Agency hoped to deliver 33% of water bodies in good status by 2015, but progress has been slow, and our assessment of our water bodies shows that they stubbornly remain at about 25% in good status. This illustrates how difficult it is to change the water environment. And for lakes in particular, we need to consider all available measures, and I welcome the opportunity this conference provides to think about and evaluate the in-lake approaches in addition to catchment management. I want now to return or to say something more about a case study I've been involved in for the last 40 years. This is in the Norfolk Broads, and I want to illustrate here some examples from Barton Broad and the River Ant. In this case study, we took phosphorus from sewage works out of the catchment in 1980, where the red arrow is. We saw initial rapid reduction in lake phosphorus, largely because the spring levels reduced quite quickly. What we found, though, was that the summer phosphorus remained high, and we noticed the change stabilized at the end of the 1980s. Note the way the blue line, which is a GAM model, reaches an apparent plateau in around about 85, 86. We decided that sediment phosphorus was the most likely explanation and began to do more work on it. We took sediment cores to investigate this using experimental work. So we took cores, put them into a growth chamber to measure phosphorus release rates. And you see results of experiments in 1988 here on the left. During the winter, there was net retention of phosphorus in the lake, but from May through June, July, August, significant phosphorus release. And if you compare it with the box showing the external loading at the far right, you can see that the internal loading was several orders of magnitude higher than what was arriving from the catchment. The solution then, we felt, was to remove the sediment from the lake. We were able to do that using a suction dredger because the sediment in Barton Broad is relatively fluid, has a high water content. So between 1996 and 2001, the suction dredger moved up and down the lake, pumping the liquid sediment out, depositing it into a series of lagoons on some agricultural land behind the lake some distance away. There, the water was allowed to evaporate and run off, and eventually the dried sediment was returned to agricultural use. The result was a significant reduction in phosphorus in the lake. See now, if you look at the plot here with the arrows marking the period of sediment removal to the right, phosphorus levels are now very near the good moderate boundary. So, suction dredging in Barton Broad, was it a success? Well, it certainly removed a significant reservoir of phosphorus. It had substantial benefit of increasing water depth. Remember, it's a very shallow lake of only about 1 metre. The phosphorus concentration, and if you know, the plankton biomass declined substantially. However, we also had some evidence that lake sediment was re-equilibrating by 1995, some 15 years from the start of phosphorus removal. If you look at the graph on the top right-hand side, you can see the relative rates of phosphorus loss in each of the years, 87, 88, 90, 95, and then just immediately before the end of pumping in 99, when we took samples from the undredged and the dredged areas. Phosphorus release rates had clearly declined, and if we look at some of the nutrient budgets we also constructed during the same period, it looks very much as if the lake went through a phase in the mid-80s of enhanced release as the lake readjusted to the lower internal loading, exchanging its sediment phosphorus pool with the water and slowly reaching a new equilibrium. Another complication was that from 1999 onwards we had much higher rainfall and river flows were substantially higher. This was the same period after which we were evaluating the changes after the phosphorus removal after the mud pumping period, and it's very difficult to draw firm conclusions. What we do know is that the experiment was very expensive. It had definite benefits, increased water depth for recreation, we removed substantial amounts of phosphorus, but nonetheless we need to be certain how effective it is. We've also done sediment removal from small isolated lakes. Here, Alderfen Broad is a small, very shallow lake with only a local diffuse phosphorus source as input, perhaps a few septic tanks. In 1979, the inflow stream to this lake was diverted to run around the edge of the lake as an attempt to restore the lake. What we found, however, was that after that, phosphorus levels increased dramatically, and we ended up with substantial problems, very shallow water. In the hot summer of 1990, we had a fish kill, and the lake was by no means restored. So again, we started to have a sediment removal process, mud pumping the lake between 1992 and 1993, after which phosphorus levels declined substantially. Following that, there was a significant recovery of macrophytes. And of course, when interpreting these sorts of data, one is always in the situation of trying to determine cause and effect. There's evidence there that the phosphorus levels after mud pumping were much lower, but the significantly lower values didn't occur until 2000 when macrophytes began to return. Was it there to reduce phosphorus reduce phosphorus from release of sediments, or indeed uptake of phosphorus by the macrophytes? Quite difficult to determine, and we need more research. What are the alternatives to mud removal? Well, of course, it's dosing of the sediment to help retain the phosphorus. However, it's important to understand the mechanisms. In the Broads, we decided that dosing with ferric chloride by direct injection to the surface sediment might be successful. It had been used experimentally in the Netherlands with some success. So we started trials on this, both in the experiments in the lab and subsequently in ran with Broad. In the lab, results are very encouraging. We see here a plot on the right showing the effect of introducing iron into an experimental core system with a flow through release rate measurements. And you see that in the middle, when we added the iron, the phosphorus loss rates were quite significantly reduced. We went on to try out the same thing in a lake, dosing a substantial area of the lake with iron. However, immediately after the dosing, we could see elevated levels of iron in the surface 4 or 5 centimeters. Look at the top row of plots here, which show the distribution of iron with depth. However, within 4 months, the bottom row, the iron peak in the surface layer of the sediment largely disappeared, and we were unable to show any effect at all on phosphorus release rates by taking experimental cores from the dosed or the undosed areas. So you need to understand the mechanisms. Iron is an important element in retaining phosphorus in the sediment when it's oxidized, but in the Broads, the sediment becomes anaerobic, and by early summer, even the surface sediment can have very low redox and effectively becomes anoxic. We see sulfide production, which allows phosphorus to be displaced from the phosphorus binding sites with iron as a result of iron sulfide forming. So what we learned from these experiments, we should have known perhaps, was that iron was not an appropriate method of binding phosphorus in lakes of this type. However, there are other binding mechanisms, and I don't wish to go into those. I have no experience of it. That's the subject for the rest of this discussion in this conference. But I want to remind you of the effects on the biota and the effects the biota have or potentially can have on phosphorus release rates. During our work, we discovered that bioturbation can have very significant effects on phosphorus release. I show you here a set of an experiment, again, which is an experimental setup to measure the phosphorus release from cores. Where the red arrow is, we added chironomids to these cores, and you can see in the top line a substantial increase in the phosphorus release rate after these animals were added to the core. We're fairly confident that actually bioturbation can greatly enhance the release of phosphorus. We also noticed that the peak phosphorus release rates in these lakes occurred at exactly the same time as the peak numbers of the large fourth instar larvae of these chironomids. Also, there can be unexpected consequences of manipulations by engineering, if you like, of lakes. This lake here, Ormesby, we did a biomanipulation. We attempted and succeeded in removing most of the fish from the lake. What we didn't expect to see was a change in the phosphorus as a consequence of that. So in 1995, the majority of the fish population from this lake was removed and has remained isolated ever since. What we saw was a very substantial increase in the levels of phosphorus during the summer after that biomanipulation. We don't have a full explanation of that, but it's almost certainly a result of enhanced sediment release. We don't know the exact causes, but my hypothesis is that the effect of removing fish had substantial knock-on impacts on the numbers of chironomids in the sediment of this lake, and that through bioturbation we have altered the extent of phosphorus release. So when you change lakes, you can have quite unexpected consequences. So in summary, control of eutrophication is clearly a priority. When we do that, we need to think first about reducing phosphorus at source. It has to be the first consideration. However, the impact of phosphorus stored in the sediment is an issue that can't be ignored. With the very delayed recovery, which in fact depends on how long the sediment phosphorus pool takes to be reduced, that itself is a function of the rate of release and the rate of water exchange in the lake. So in most lakes, phosphorus release occurs during the summer. If there is a good deal of flushing during the summer, then much of that phosphorus will be removed from the lake system. If, on the other hand, the flushing rate is very low during the summer, then most of the phosphorus will simply return to the sediment. So flushing phosphorus from the water is quite quick. Flushing phosphorus from the sediment is quite slow. We need to think about how long that process is likely to take. That brings me on to thinking about the appropriate selection of lakes. When we're considering bioengineering type approaches, we need to think about the relative importance of internal and external loads. Have we taken sufficient action to reduce the sources of phosphorus before we go into geoengineering type techniques? Indeed, do we want to, in fact, restrict the amount of phosphorus being released, because that will slow down the natural re-equilibration of the lake? There may be situations where actually being patient and awaiting the phosphorus release to restabilize, say after 10 years, is in fact a preferred solution. However, sediment removal has multiple benefits. In recreational lakes, particularly very shallow ones, the increase in water depth may well be the most important reason for removing the sediment, and phosphorus then becomes a benefit. Sediment dosing may well be an alternative, but we need to think about how appropriate the binding mechanisms are, making sure they're not sensitive to redox change. How long will the effect last? What is going to be the effect of physical mixing? And then lastly, as I've said before, we need to think about what the impact on the biota is. Are there going to be changes from the dosing or anything else we do that might influence that? Lastly, I think we need to think about what we're aiming to achieve. In some lakes, we may well be interested in conservation value. We strive to take the lake back to its ultimately high or even, well, perhaps good status. Elsewhere, we may just be looking for cost-effective solutions to ensure that the recreational use of the lake can be achieved. Whatever we do, we're looking for cost-effective solutions. So I want to leave you just with my final thought, and that is that restoration should not be treated as a quick fix. In my opinion, we need to take a long-term view. Ultimately, we have to deal with the causes, and you already have heard, I think, from Brian Moss that geo-engineering is essentially an aspirin. Well, aspirins can be quite helpful to aid recovery. They're probably not the ultimate solution.